In this video, we're going to turn our attention to the question of how to multiply two vectors together. This is not going to be the same as scalar multiplication because scalar multiplication took a vector and a number, a scalar. So there's actually two ways that we're going to talk about. Both of them will have their advantages and their uses, but neither one of them is really going to really capture the idea that you probably expect. Because this is just going to be a little bit more complicated. You could imagine, say, taking two vectors, so maybe a vector v, which is v1, v2, and try to multiply it by a vector u, which is u1, u2, and try to say multiply them component wise. So take v1 times u1 and then v2 times u2 and say, well, that's just the way we add vectors. Why don't we multiply vectors that way? We could theoretically define something to be that, but it turns out this definition is just not very useful. There's nothing that we can really do with this. For one thing, it really doesn't mean much geometrically. So we're not going to use that. Instead, maybe I'll write over here. This is not useful. Instead, we're going to define what we call the dot product. This will take two vectors and multiply them together, and instead of getting another vector, we're going to get a scalar. So two vectors are going to multiply to get a number. So here we have two vectors, a and b. We're talking about two vectors in three-dimensional space, a1, a2, a3, and b1, b2, b3. The dot product of those two vectors, essentially, we are going to multiply the corresponding components, so a1 times b1, a2 times b2, a3 times b3, kind of like what we're doing up here, but we're going to add those together, which might seem a little weird to do at first, but it turns out this is going to have some very useful and geometric ideas that are connected to it. Note that we can do this with two-dimensional vectors. If we didn't have an a3 and a b3, we just wouldn't have this third term here. And in fact, we can do this with higher dimensional vectors if we wanted to as well. We would just have more terms in that case. This does have some other names for it. Some people call this the scalar product because the result of this product is a scalar. That will contrast with another product that we're going to talk about later on in this video, which will actually result in a vector, and some people will call that one the vector product, though we'll have a different term for it. Another term is the inner product. This is a little bit more a little bit higher tier of a term for it. If you go on and take linear algebra, you'll see these terms pop up a little bit more. Basically, this is an example of a more general type of product of vectors, and so it has that more specific kind of term, inner product. But the book just sticks with dot product, so we'll just go ahead and key in and use that terminology. Now, calling this a product kind of brings in some thoughts about how it should behave, and it turns out it does really behave the way we kind of expect it to, especially when we combine it with addition and scalar multiplication. And it has various properties that are very useful. So here we have some properties. So the dot product of a vector with itself is actually, you could say it's the square of the vector, or you can just say it's the magnitude of that vector squared. The dot product is commutative. It doesn't matter whether or not we multiply in a times b or b times a, we get the same result. That's pretty easy to see if you just look at our definition. We just have to swap the orders of each of these three products. It actually does obey a distribution rule with addition. It distributes over addition. Note here, this is addition of two vectors, whereas here it's addition of two numbers, because a times b and a times c are both numbers. It obeys sort of an associativity when it comes to scalar multiplication. So these are actually two different types of multiplication, but it does actually allow us to move the parentheses around the way we might expect. And also, the scalar c can actually move to either one of the terms if we're doing this. And finally, if we're working with the zero vector, remember the zero vector is just the vector of all zeros. So you could say in this case, if b were the zero vector, we'd basically be replacing b1, b2, b3 with zeros, and so we get 0 overall. So exactly the way we might expect it to behave. But those properties are not why we find the dot product useful. So what we're going to do is, now I'm not going to go ahead and prove this. In some later sections when we actually are focusing on less review and actually introducing new material, I might have gone ahead and proven something like this. But for now, I'm just going to go ahead and give you the formula. So here we have two vectors. We have a vector A and a vector B. And this works in both 2 and 3 dimensions. You can imagine these vectors being in 3 dimensions if you want to. But if we have two vectors and we put their initial points at the same point, they form an angle. And technically, even if these were go the same direction, the angle there would just be 0 degrees. Or if they go in opposite directions, the angle there would be 180 degrees or pi if you use radians. And so we have a theorem that says that the dot product of these two vectors is going to be the products of the magnitudes of them. So the length of A times the length of B times the cosine of this angle. And this just comes from the law of cosine. So if you go back to trigonometry, there's a law of cosines dealing with angles of a triangle versus the lengths of the sides of the triangle, and we can actually use that to prove this result. But I'm not going to go ahead and do that right here. It's just kind of a little bit, it gets a little bit messy, but going through the work, but it's actually rather straightforward. But this is what the importance of this. The dot product, it essentially tells us the angle of between two vectors. In fact, most of the time we'll go ahead and solve this equation for the cosine and use the dot product as a way to find the angle instead of, say, knowing the angle and trying to find the dot product. So this is what we get when we actually solve for the cosine. So let's actually do an example of this. So maybe take an example from the book. Let's go ahead and work out problem 17. So here we're given two vectors. Vector A is 1, -4, 1. Vector B is 0, 2, -1, or -2, sorry. We want to find the angle between these two things. We can use whatever initial point we want. We imagine that we're working with two vectors coming off of the same initial point. We want to find that angle between those. That's pretty hard to think about right away. Even if we drew a picture, that might be pretty hard to actually see what's going on, or even have an idea of whether or not it should be an acute angle, an obtuse angle, maybe they're perpendicular. We have no idea. But using the dot product, it's actually really easy. So we're going to compute the dot product. That means we'll take this 1 times 0. Then we add -4 times 2. So our y components. And then our z components. So we have 1 times -2. course, this becomes a 0. We have a negative 8 and a negative 2. So ultimately, we can have a negative 10. That actually tells us something about it already, but we'll get to that. But we also do need the magnitudes of a and b. Remember, the magnitude we compute by taking the square root of the sum of the squares. So we have 1 squared plus 4 squared, and we leave off the negative, plus 1 squared. So we have the square root of 16 plus 1 plus 1, so square root of 18. And I guess we could actually simplify this. So 18 is 9 times 2. The 9 we can pull out to be a 3, so 3 radical 2. We do the same thing with b. We have 0 squared plus 2 squared plus 2 squared. That means we have 4 plus 4, so we have square root of 8. We can actually pull out a 4, so we have a 2 radical 2. That means that the cosine of the angle between them is going to be the dot product of negative 10 divided by the product of these. So we have 3 radical 2 times 2 radical 2. That's actually kind of nice. The radical 2's can combine. We're going to have 3 times 2, but then the 2 squared root of 2 will be another 2. So 3 times 2 times 2 will give us a 12, though we actually can divide out one of those 2's with a 10, so we'll get a negative 5 over 6. And so whatever this angle is, its cosine is negative 5 over 6. And one of the nice things about this formula is that the cosine, as long as we're considering the angle to be somewhere between 0 and pi, the cosine is unique. We don't have to worry about trying to figure out, well, what is the, do we actually have the correct angle or not? We can just plug it in, put negative 5 over 6 into our calculator, take the inverse cosine, and it'll spit out the right number, depending on whether you have it in degrees or radians and what you're expecting. But we can go ahead and whip out a calculator and find this out. So what I got was that the angle is going to be, in radians, it'll be 2.556 approximately. Or if we're going to go ahead and use degrees, it'll be 146, and let's just say 0.4 degrees. And that will be our answer. The angle between these two vectors, regardless of whether the fact that we're working in three-dimensional space, is actually about 146 degrees. Now, I mentioned a little bit before that I kind of had an idea of how big this angle is going to be already. And that comes from the fact that when we worked out the dot product, we got a negative number. Keep in mind the magnitudes of a and b are always going to be positive numbers. Therefore, whether or not the cosine of theta is positive, negative, or 0 only depends on a and b, on a dot b. So once I knew that the dot product was a negative number, I kind of had an idea of how the cosine would behave. Remember, cosine of an angle between 0 and pi over 2 is a positive number. Cosine of pi over 2 itself is 0, and cosine of an angle between pi over 2 and pi is negative. So once I found out that this was negative, then I knew the cosine of theta was going to be negative. So I knew theta was, no matter what, was going to have to be a number between pi over 2 and pi. It had to be an obtuse angle. 146 degrees is an obtuse angle. And that's a pretty useful thing to know. But it also means that if the dot product of two vectors is 0, because cosine is 0 for just pi over 2, assuming we're not working outside of that range, then we automatically know that those two vectors are perpendicular to each other, that the angle between them is pi over 2. So we actually will call, I didn't leave myself as much space as I should have, but if a dot b equals 0, then theta is pi over 2. So they're perpendicular to each other. But we call this, so we call a and b orthogonal. Because for some reason we have to have a special term for perpendicular when it comes to vectors. But orthogonal is pretty frequently used in the realm of vectors instead of the word perpendicular. If you say perpendicular, most of the time people will know what you mean. Just be aware that orthogonal is a pretty commonly used term, and there's various terms that are derived from the word orthogonal. But we might not really run into a lot of those in this course. But if you do take a course in linear algebra, you'll see a lot about orthogonal vectors. But just be aware that all you need to do to actually know whether or not two vectors are perpendicular to each other is know that the dot product equals 0. It's just that easy. The next type of product that we're going to talk about is called the cross product. The cross product has the advantage that if we take two vectors and multiply them together, we actually do get another vector out. So here we have the vector a1, a2, a3, and b1, b2, b3. When we take their cross product, we get this vector where the first component is a2, b3 minus a3, b2. Second component is a3, b1 minus a1, b3. And the third component is a1, b2 minus a2, b1. We get a vector. Unfortunately, it is a fairly complicated definition. It's kind of hard to remember it. And so that's one of the big issues with it. The other issue that may not be as obvious is that this is specifically a product that works in 3 dimensions. There is no 2-dimensional equivalent to the cross product. So that is a major problem with this being a matrix, a vector product. It's very specific to 3 dimensions. But it has some very useful applications that means we definitely need to have this product to be able to do stuff. In fact, physics uses this kind of thing all the time in order to do various things. And we'll get into exactly why that is in a moment. But first, I do want to kind of address how we might remember how to take a cross product. So I don't want you to just memorize this formula. That's kind of just really complicated and not really too useful. One way people remember this is by using matrix determinants. And if you don't know much about determinants, do not worry too much about that. I will show you another way in a moment, but I'll have to actually get through some stuff, motivate some stuff before we actually get to that. So here, using the same a and b that we have up here, what we do to take their cross product is write down a as a second row and b as the third row of a 3 by 3 matrix, and then put our standard basis vectors I, j, and k as our first row. And then if you know how to actually find the determinant, you would follow that formula. Technically, this is a little bit abuse of notation because we are putting vectors in the spots in this matrix. It's a matrix that's somehow composed of vectors and scalars. That's a little bit odd, but the formula that we follow does work the way we expect it to. Let's actually do an example of this. Let's use the a and b that we had on the previous page. So we had a was 1, -4, 1. B was 0, 2, -2. And we'll go ahead and take the cross product of these. So A cross B, we'll have I, J, K on top. We have 1, -4, 1 as second row, and then 0 to -2 as our third row. we'll go ahead and expand this along the top. If you remember the cofactor expansion of the determinant, we basically look at this I, remove the first row and that first column, and then we'll multiply it by the determinant of what's left, so the negative 4, 1, 2, negative 2 times I. The next one we unfortunately have to have a minus sign, but then we do the same thing with the j, where we take out the first row and the middle column, and we take the determinant what's left. We have 1, 1, 0, negative 2 times j. And then finally with the k, we take out that first row and that third column, and we take the determinant what's left. We have the 1, negative 4, 0, 2 times k. To take the determinant of this 2 by 2, we essentially cross multiply, so negative 4 times negative 2 will give us 8, but then we subtract 1 times 2, so 8 minus 2 will give us a 6 times I. Then here we do the same thing, 1 times negative 2, but then minus, well, this is just 0 when we take 1 times 0. So you get a negative 2, but with that negative that's already there, we get a plus 2 times j. Finally, we do the same thing here. 1 times 2 is 2, but then we get a 0 for that part, so we get a plus 2 times k. Or if we go ahead and write this as in our angle brackets, and technically we could leave it as in terms of I, j, and k if we want to, but since we start out with angle brackets, let's put it back into angle brackets. The cross product of those two vectors is 6, 2, 2. Now, what really is the point of the cross product? Well, it's this theorem right here. The vector A cross B is orthogonal to both A and B. Essentially, by taking the cross product of two vectors, we find a new vector that is perpendicular to both the original two vectors. That means essentially what we're doing here is we have an A and B. So remember here we're working in three-dimensional space. So imagine these are sitting here in three-dimensional space somehow. We take their cross product and we end up with something that is perpendicular both to A and to B. Now A and B didn't have to be perpendicular here, so they've got some, I'm imagining there's some acute angle between those two, but we got a new vector that is perpendicular to both of them. And that is a very useful thing to be able to do. Now, there is some things that we might have to think about here. If we just take two vectors, we could think, well, there's a vector going this direction that could be the cross product, or it could be going the other way. There's a line that's perpendicular to both of them, but which direction do we go along that line? And that's where our right-hand rule comes back. Remember our right-hand rule that we talked about in the first video when we talked about how we orient our axes, which axes we pick to be x, y, and z. Well, we're going to use the same idea here. So remember we have A then B. So we're going to take our right hand, specifically the right hand, put our fingers in the direction of A, curl your fingers towards the direction of B, and if you do that, your thumb will have to be in the direction of the cross product. Note that if you swap the order of A and B, it actually reverses the direction of the cross product. So here, the way I've drawn this, I would put my fingers along A, curl towards B, and in fact here, A cross B is in the correct direction for our right hand. But if I were to do B and then A, I'd have to curl my fingers this way, and I'd have to go the opposite direction. So that kind of brings up a interesting point where swapping the order of A and B actually changes the cross product. This is not something that is commutative. And we'll discuss that in a moment. I'll write down a bunch of properties for this. That tells us the direction. It's also useful to be able to compute the magnitude as well. So here we actually have a formula for the magnitude of the cross product. The magnitude of the cross product is actually related to the angle between the two vectors as well. This one's a little less useful for computing the angles for a couple of reasons. First of all, the sign actually is kind of ambiguous when it comes to angles between 0 and pi. Sign will always be positive in that range, and so you have to be a little bit careful about it. Knowing what the sign is only gives you a choice between two angles, and you would have to determine which one is correct. And the cross product is harder to compute anyways. So the dot product is usually the one that's used for actually computing angles, but this is a way that we could talk about the magnitude of the cross product without having to actually compute the cross product if we prefer. Usually I'm not going to go ahead and use this formula, but it is useful to know that it exists. Another useful result from this formula is that if we have our vectors a and b, and we actually complete a parallelogram, kind of like how we talked about how to form the sum, where the here we essentially make a new copy of a, and we make a new copy of b, and we form a parallelogram like that. The area of this parallelogram is actually the product of the two sides times the sine of the angle between them. So in fact, the magnitude of the cross product is exactly the area of this parallelogram. So you can say area equals the magnitude of the cross product. And that's a useful result that actually comes into play a lot when we get into some things involving integrals later on. So we'll see this idea, maybe not work with it maybe explicitly, but the idea that this actually is related to areas is very important for why some of the formulas that we'll have later on are correct. But for the moment, we don't really have to do a lot with that. Let's actually look at some of the properties of the cross product, though. They're going to be similar to what we expect, but there's going to be a little bit of a twist there. We already talked about how the law of commutativity doesn't really hold, but let's see how that actually plays out. So here we go. So if we swap the order of the cross product, we end up getting a minus sign. The sign of it changes. So it's not too bad. It is pretty straightforward to be able to swap A and B, and it doesn't change it too much. It just changes the direction. It actually doesn't change the magnitude at all. It does actually kind of associate with the scalar product. It's actually pretty nice that way. And in fact, if you look at property 5, it kind of works with the dot product as well, though it is a little bit tricky. Notice here that we cannot take the dot product of a vector with a scalar, or the cross product of a vector with a scalar. So it doesn't work directly. Which one's the cross product, which one's the dot product switches when you do that. But there is kind of a rule here. The cross product does associate with, not associate. It distributes over addition in both ways. So these are 3 and 4 are essentially the same rule, but just which side we put the cross product on. And really the proof of one kind of follows from the other one, just because we can just introduce a minus sign and swap the order if we wanted to. Property 6 is kind of nifty, I guess. I've never seen a use for it, or at least maybe not directly. It's listed there, so I've included it. But the main rules that we can distribute over addition and pull out scalars and all that kind of stuff. Those are what are really important for us. And they're going to actually help us do some computations of cross products without having to necessarily bother with determinants if that's not your cup of tea. Now, one thing that that this doesn't say, and I kind of wish it did because it's actually pretty important. What is the cross product of a vector with itself? Well, remember, if we swap the order of the cross product, we get a minus sign. So if we swap A with A, which doesn't really change anything, we should still introduce a minus sign. A cross A has to equal negative A cross A. Well, what's a vector that is its own negative? Well, similar to regular numbers, what that actually means is that A cross A has to equal the zero vector. So here, this is the zero vector. This is 0, 0, 0. That is fixed. Any vector crossed with itself is always a zero vector, no matter what. And actually, if we think about it, that makes sense. So remember, A cross A, or its magnitude, has to equal the magnitude of A times the magnitude of A times the sine of the angle between. Well, the angle between A and A is 0 degrees. They're the same direction. So sine of 0 is actually 0. So the magnitude of A cross A, regardless of what the magnitude of A was to begin with, has to equal 0 anyways. And the only vector with a magnitude of 0 is the 0 vector. So that's actually pretty important. In fact, that's an easy way of checking whether or not two vectors are pointing in the same direction. If two vectors are pointing in the same direction, they have a cross product of 0. In fact, if they point in opposite directions, if they're pointing directly opposite each other, they form an angle of 180 degrees, or pi radians, and that sine is still 0. So they still have a cross product of 0. Of course, that only works with three-dimensional vectors. So it's useful there at least. Alright, so these properties are going to be useful for computing the cross product by looking at what happens to the standard basis vectors. So remember the standard basis vectors. I, j, and k. And think about what would happen if we take their cross products. Now I'm just going to go ahead and give you the result. It turns out if we take the cross product of two different standard basis vectors, we get either plus or minus the third standard basis vector. So I cross j is equal to k. Of course, j cross I is equal to negative k, because switching the order changes the sign. And similar for the other ones. What the book doesn't show here is that if you take the cross product of I with itself, and j with itself, and k with itself, we just get 0. Again, I don't know why they don't make a bigger deal about that, because it is kind of important that happens. Now, one thing I like to do to help me remember this is kind of think about a circle. So we kind of have an order to these. We have I, j, and k. So this is the order of x, y, and z. So I to j to k to I. And what we do, if we remember this kind of a circle, is if we're taking the product of two of these vectors, is try to see if you're following the arrows or not. If you start with I and you're multiplying it to j, we're following the arrows. And we continue following those over to k. But since we're following the arrows, it's going to be a positive k. If we're taking, say, k and then multiplying it to j, we're going opposite the arrows. We end up with at I, but it's a negative I. So k cross j is negative I. So if you remember how the circle goes, and remember that the product of a vector with itself is 0, then that makes it really easy to compute cross products. So let's actually do an example of this. Let's just go ahead and use problem 1 of section 12.4. So here they give us a vector of A is 2, 3, 0, a vector B, which is 1, 0, 5. In fact, having zeros here will show how this actually makes it a lot easier when you do have a lot of zeros. Notice that what we can do here is change this into something that involves I and j. Or ij, technically ij and k, but we have a 0 here, so we don't need the k. This one is just I plus 5k. So if we take the cross product of A and B, then we're taking the cross product of 2I plus 3j with I plus 5k. We can go ahead and actually distribute, just basically FOIL this out the way we normally would. So you have 2I times I, 2I times 5k, 3j times I, 3j times 5k. We do have to make sure that we don't change the order of the vectors when we multiply them, but we can pull out any of the scalars. So here we have 2I times I, so we have 2, but then we have I cross I. We'll simplify these in a moment. We have the 2I plus times 5k, so the 2 and the 5 we can pull out to get a 10. Then we have I cross k. Then we have the 3j and the I, so we can pull out the 3, and remember the j was before the I, so we have to keep them in the same order. And then finally we have the 3j and the 5k, the 3 and the 5 combined to be a 15, and then we have a j cross k. So that's the first step that we do. Now we simplify these. So first things first, I cross I is 0, so that's gone. So we don't need that one. And then we have to worry about what the other ones turn into. I cross, and actually let's go ahead and put our circle here. I'm used to it enough that I don't really have to draw it out to remember it, but just to help us out if you are not as familiar with this at least. We do I cross k, so I to k, we're actually going against the arrows, so we have a negative j. So we're going to have a negative 10j. I'm going to go ahead and put that in the middle for now. J times I, so j to I, again we're going against the arrows, so we'll get a negative k. So this will actually turn into a negative 3k. And then finally j cross k, we're going with the arrows this time, so we get a positive I, so we have a positive 15i. Or in other words, if we want to write it back in angle brackets, which again you don't have to do, but you can, it's going to be 15, negative 10, negative 3. So, pretty easy as long as you remember the way of actually working out what the cross product of two standard basis vectors is, no matter which order they are in or whether or not they're different or not. If you remember that process, you don't even have to worry about doing the determinant. Do note that in general, you won't have these two zeros here. The two zeros meant that we only had 2 terms times 2 terms. Normally you'll have 3 terms times 3 terms, which means instead of 4 terms here, you're going to have 9 terms. And, well, 3 of them will always go away because you'd have I cross I, j cross j, k cross k, but then the other ones will actually stick around, and they might combine. You might have an I cross k term and a k cross I term. And those will both turn into a j or a negative j, and you'll have to combine those before you actually move on. But most of the time, it's easy enough to know how to do that. It shouldn't be too hard to realize that 5j plus 2j is 7j. That pretty straightforward. Now, one thing I will note that in the online homework, so this is specifically about the online homework, when you're inputting your answers, you can either, well, pay attention to the directions. Some might specify one way or the other, but if you put them in angle brackets, there should be a button on the toolbar to put in angle brackets. You don't use the less than or greater than signs on your keyboard. Those are not correct. Also, this one's a little trickier. The I, J, and K, you cannot use the buttons on your keyboard for those ones either. You also need to be using the ones in that same toolbar. If you put the ones from your keyboard in, it will count them incorrect, and you're going to be really confused. So be very careful about that. It's one of the quirks of WebAssign. I'm a little bit annoyed by it, but it is the system that we have. So if you run into any problems like that, either remember this, or you can always send me an email about it, and I can point you in the right direction. Or you can send me a message through WebAssign as well. But just be aware of that. But I'm going to leave this here. I know I kind of spent a lot of time on these sections, but kind of wanted to get through these rather quickly. I didn't want to spend a lot of time on these sections when they're supposed to be a review, at least. In the next videos, which I'll have up in a couple days maybe, we're going to look at 12.5, and that will be, and these first 5 sections are going to be on our first homework. 12.5 will actually put to use a lot of the stuff that we've been doing with the dot product and cross product in order to actually look at the equations of lines and planes. So it'll be kind of application of the stuff that we've been doing, but also learning about how surfaces and stuff that we're going to be working with will work. So I'll see you in the next video.